We present the first controller for quasi-static robotic planar pushing with single-point contact using only force feedback to sense the pushed object. The controller does not know the geometric, inertial, or frictional properties of the pushed object, which we call the slider, nor does it get measurements of the slider's pose. The controller computes a pushing angle theta p using the law shown here, where theta d is the desired pushing angle, delta F is the difference between the sensed contact force angle and the desired angle, delta C is the lateral path offset, and Kf and Kc are positive tunable gains. The corresponding end effector velocity is simply a constant vector in the computed direction. We also include mechanisms to recover contact if it is lost, and an admittance controller to regulate force in the presence of obstacles. Please see the paper for more details. We use an omnidirectional mobile robot equipped with a force-torque sensor at the wrist of the end effector, as shown here. We perform experiments pushing a box and barrel slider, each of which contains 2.25 kg weights. We demonstrate pushing along straight and curved paths, including one with a static wall obstacle. In this first experiment, we push the barrel slider along a straight path. The sensed contact force, in polar coordinates, and the positions of the desired path, slider position, and end effector position are shown in the plots. Next, we push the box slider along a curved path. Notice that there is some overshoot at the turn, but the controller steers back towards the path afterward. Now we perform the experiment again, but this time with a wall obstacle. Notice that the slider makes contact with the wall, but the controller adjusts to continue along the path. An admittance controller helps regulate the force during contact. Next, we show that our controller can easily adapt to perturbations of the slider, such as a change in its inertial parameters. First, we see what happens when one of the weights is removed from the box, changing its pressure distribution. The controller quickly adjusts the contact point to push with this new arrangement. Ignore the noise in the slider position plot due to the box's lid being moved. Next, the barrel is manually moved while being pushed. The controller adjusts to push it back toward the desired path. Finally, we show a simulated example of the contact point switching faces on the slider. Here, the pusher is a red sphere and the slider is a blue box. The slider contacts the wall and the contact point actually switches from one face to another, and then the push continues successfully. Thank you for watching.